In this video, we're going to talk about sets. So let's talk about what a set is when we define one mathematically. So a set is a collection of objects that's well defined. And what I mean by well defined is meaning you know what's in this set based on either my description or by actually seeing a list of what is in the set. Let me give an example of a set. Let's say I want to do the set of all of Allison's pets. All right. Now, you may not know this set, but I know this set. And here I'm going to list the pets I've had. Let's see, I had a fish named Bruce, a bird named Louie. I had a previous dog who passed away named Katie, and my current dog, Teddy. So the list of all of the members of this set like this, I typically enclose it in squiggly brackets. That's on purpose. We have a special notation when we list out sets in mathematics, and it's using these squiggly brackets. By the way, this notation that I'm using here, this is called roster notation. And the roster notation is basically listing out members of the set. All right. Okay, now real quick, important definition for this. We call the list of everything in the set, or actually, let me start with this. So DEF for definition, okay? So I'm going to define this. So an element is what we call a member of a set. So in my example here of Allison's pets, an element would be Louie, because Louie is a member of the set. So this is an element of that set. All right. So that's an element. The list of everything in a set, we call that a sample space. So the complete list of elements in a set is called the sample space. Oops. Let me go ahead and underline the words. Let me actually put definition, sorry, not a star. So I'm defining some things here. Okay, so the complete list is this list right here. So this right here would be my sample space. All right. Okay, so good. Got some terminology under our belt here, just so we can kind of discuss it. Let me give some other examples of sets. Let's say the set of all US states. And if I wanted to list out all the states, maybe it'd be wise to do it in alphabetical order. So I'll start with Alabama. And then it's Alaska. Next is Arizona. Okay, now I'm not going to list out all 50. So ... Wyoming. There we go. That would be a list. So the ... implies follow the pattern. It could also imply infinity. Let me give you an example of that. Let's say I wanted to list the even numbers. So I would start my list at 2. Most people say 2, 4, 6, 8, 10, and then dot, 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 because it keeps going on forever. Okay, now, let me give a little bit more terminology here before we get into some important sets. So we can have smaller versions of a set. So for instance, let's go back to the US states, okay? For the US states. Oh, here, let me define really quickly. My apologies. What I was about to define. So a smaller set would be called a subset. So a subset is a set whose elements can be found in another set. And it's typically another bigger set. I'll use that in quotes, bigger set. So everything in a subset can be found in a bigger set. Let me give you an example again. This time I will use the US states. So, let me move down to the next page. So a subset of the set of all US states would be, let's say, the West Coast. Actually, here, let's do this. Let's say the states that touch the Pacific. And I'm referring to the Pacific Ocean. All right. So we can list those states. Those states would be California, Hawaii would count, Alaska would count, Oregon, of course, and then Washington. So we have 5 elements in this subset. And since all 5 of these can be found in the big set of US states, this would be a subset of that set. Okay, you kind of get the idea. Now I'm going to kind of move into numbers and work with numbers from here on out. Before I do that, I want to give us some important sets that we should probably know. Sets of numbers. And you've probably heard of a few of these. The first is what's called the natural numbers. Those also can be referred to as the counting numbers. Oops. Counting numbers. It's like what you teach a kid. And those numbers would start at 1, 2, 3, 4, 5, dot, dot, dot. And they go on forever. They don't end. All right, so there's the natural numbers. Then we have the whole numbers. So the whole numbers are the exact same as the natural numbers, except they include 0, 2, 3, 4, 5, and so forth. So they have everything the natural numbers have, but they also have 0. So the natural numbers would be a subset of the whole numbers based on that terminology we just talked about earlier. Okay, let's see. Integers would be next. Now, integers are described as positive and negative whole numbers. So they start with our negatives. And for that reason, we actually have a dot, dot, dot going in both directions. So it'd be like -3, -2, -1, 0, 1, 2, 3, and then dot, dot, dot off to positive infinity. So the first dot, dot, dot means we go off to negative infinity, and the second one is positive infinity. So there are the integers. Then we have the rational numbers. Now here's where it starts getting more complicated. I will not be able to do roster notation for natural numbers. I'm sorry, rational numbers. I will do a descriptor, and here's the descriptor. These are numbers that can be written as fractions. And then it does contain certain types of decimals that actually can be written as fractions. So those decimals happen to be finite decimals, meaning like 0.5 is an example of a finite decimal, or repeating decimals, like 0.3 repeating. So I'll write my two examples down there. So a finite decimal is a decimal that stops, and then a repeating decimal goes on forever, but it repeats the same number. And those are considered rational numbers because those are numbers that actually can be represented as fractions. And if you didn't know, 1/3 is 3 repeating. If you put it in your calculator, you'll get 3 repeating. Okay, so there's rational numbers. Super exciting. Irrational numbers are basically everything else. They are not rational numbers, but we typically describe them as infinite decimals that never repeat. Now we have some famous examples of those. The most famous would be pi. Most people know that pi is a number that goes on forever but never repeats, 3.1416, blah, 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 blah. And we will look at in chapter 2, the number e. E is 2.718, blah, blah, blah. It's also a non-repeating decimal. It's an irrational number. Another really popular example are square roots of numbers that you can't take the square root of, like the square root of 2. That would be a decimal that doesn't repeat. Okay, so these are examples of irrational numbers. They're kind of not pretty. They're basically everything else that isn't a rational number. And then the last set that you've probably heard of are the real numbers, and they are everything, both the rational and irrational numbers. And irrational. Awesome. So we've most likely heard of real numbers, integers, maybe even whole numbers, but these are kind of the list of all of these so that you can kind of see how we define them. All right, so there we go. We've talked about some of the important sets. I do want to do some more examples with sets really quick. And we're going to kind of build off of some more interesting terminology. Okay, so let's say I want to look at the set of outcomes for rolling a 6-sided die. So that would basically be the numbers from 1 to 6. Because those are the possible outcomes you get when you roll a 6-sided die. So those would represent all those possibilities when you roll a 6-sided die. Cool. Okay, so a subset of this, and here, let me give this a label. I'm going to call it S, just so I have something to kind of refer back to. Okay, so let's list a subset of S. Oops. Let's list a 2 element. Wow, that is the wow. Okay, let's do this differently. A 3 element set or 3 element subset of S. Okay, there we go. So one subset would be 3 and 6. Another subset could be 1 and 5. Oh, I said 3. 3 elements, sorry. 3, let's see. Let's put them in order. So 3, 5, and 6 would work. 1, 5, and 6 would work. Now it's getting boring. 1, 2, 3. Wow, really boring. Okay, there we go. So there are 3 examples of subsets of S. Okay, now I do want to kind of work from this a little bit further. I do want to define one other very important set that we haven't talked about yet, and it's called the empty set. The empty set is literally empty with no elements. There's nothing in it. And we'll see some use for the empty set in a little bit when we start working with intersections and unions. Okay, so the empty set is a set with no elements. We use a special notation for it. It's a circle with a line through it. Some people mistake that for a Greek letter, and there is a Greek letter that looks very similar to this called phi. But it is a circle with a line through it, which is the empty set. Another common notation is the 2 squiggly brackets with nothing inside, like a space in between, but there's nothing inside, indicating that it contains nothing. So those are ways we notate the empty set. I'll use the circle with a line through it whenever I'm working with that, but we need that before we kind of move into the next part here. So here's what we're going to look at next. We're going to look at the union of sets. So a union means we combine all the elements of multiple sets together. Combine the elements of multiple sets together. Let me give you an example. So let me list out 3 unique sets. So let's see, let's let set A be, okay, we'll just have it be the numbers 3 through 8. Let's let B be multiples of 5. And here I'll even start at 0, because why not? Okay, and then let's see, how about C will be, let's let C be odd numbers. All right, there we go. 3 unique sets. Okay, so if I wanted to find a union for these sets, we do have a special notation. We use the U symbol like this to indicate the union between 2 sets. So when you have that U in between the 2 letters that are representing sets, we're saying we're combining their elements together. So let's do that. Let's go ahead. Here, we'll have a multi-part question here. So part A, let's do A union B. So A union B, I'm going to list out all the elements, and I'm going to put them in order, okay? So let's start with 0, since that's technically the smallest number, and then 3, 4, and okay, so they both have a 5 in common. I'm not going to list it twice. I'll just list 5 once. Then they have 6, 7, 8, and then we still have the 10 and 15 from the set B. And that's how we could list out the union. Now, I put it in order just because it's nicer to look at. It wouldn't be wrong if you put it out of order, but it wouldn't be considered proper. Okay, here, let's try another one. Let's try A union C now. So for that one, we would do 1, 3, 4, 5, 6, 7, 8, 9, and 11. So there we go. They had a lot in common, right? They had a 3, a 5, a 7 in common, but the rest we had to kind of list separately. All right, so there's an example of how you could find a union of sets. Now, the next concept is called an intersection of sets. And in this case, we're looking for what the 2 sets have in common. Elements, 2 sets have in common. We do have a notation. In this case, we use an upside down U to represent intersection. So how about we use the same sets here? Let me zoom out a little just so I can, oops, see them. Wow, it really jumped the page there. All right, so let's go ahead and this time we'll find, using the same sets, let's find A intersect B. So A and B, let's see, they have 3 in common, 5 in common, and that's it. Here, I'll put part B right here just so I don't have to jump to the next page. All right, let's do the intersection of, how about B and C? So elements B and C have in common. Okay, so let's see. It looks like they have 5, and that's it. They have one thing in common. Now, this would be a great opportunity to talk about the empty set. What if they didn't have anything in common? If that happens, that would be the empty set. So here, let me create a new set here. We'll call it D. Let's say D. Sorry, I'm kind of writing really big. Oops. Sorry, really small, I mean. It's going to jump a little. I'm so sorry because I'm playing with it. Okay, let's say D is 2, 4, and 6. Those numbers right there. Okay, so if I want to look at the intersection of C and D, they have nothing in common. So they would be the empty set. So here, let me come down here. I'll write that down. So C intersect D, that would be the empty set. They don't have anything in common. So that's where we could use the empty set. All right. Now, last concept. We're going to talk about complements of sets. So in order to talk about a complement of a set, you have to have a sample space, okay? So suppose S is a sample space. Oh, here, I'm like really, I should zoom in a bit here, is a sample space. And A is a subset. Here, this is a definition. Maybe it'd be wise to put that. Suppose S is a sample space and A is a subset. Then the complement of A, which we use the notation. So I'll say denoted A with a little like slash. That's called prime in math notation, that little slash like that. So we denoted A prime. Some books use a C, like they'll put A to the C. That's also a common, here, I'll put it in parentheses, a common notation used, okay? But we'll use A prime. So then the complement of A, denoted A prime, is every element in the sample space that is not in A. All right, let me give you an example of that. Let me go back to my, oh, here, sorry, let me underline really quick the complement of a set. Okay, so let me go back to my example of the 6-sided die. So we said that all the outcomes in a 6-sided die, 1, 2, 3, 4, 5, 6, and I called that S. I didn't give myself space to do that, but let me squeeze it in. Okay, there we go. Calling that the sample space. All right, so let's say A is the subset. I think one of the ones we listed was 2, 5, 6 when we did this earlier. Okay, great. A is 2, 5, 6. Okay, so then a complement would be all the other numbers. So it would be 1, 3, and 4. So 2 important things to kind of notice. A union B is S. So here, let me make a note of that. Note. I'm sorry, A union A prime. A union, its complement, is all of the sample space. I'm sorry, I like threw in a B there and I don't know where that came from. They end up being the whole sample space. And their intersection would be an example of the empty set always, because they're defined to never have any element in common. They're everything that's not in that subset. So that's how we look at complements of sets. And that is an introduction to sets.